Hello and welcome to another episode of the Oxford Online Maths Club, this time for real. My name's James and I'm joined today by Maria.
Hello, my name's Maria, as James so kindly said. I do music at New College in Oxford, and I'm really excited to be here. I can't wait to be nerdy about music. It's going to be great.
We're doing a music and maths crossover. Maria is the first... Oh, this is the first time we've had an Oxford student on who's not doing maths or computer science, or both. So we're trying something different. I've prepared some stuff about maths with relevance to music, I think, which I'm gonna check with you. And you've prepared some things about because you do some work on. You were telling me about your work with maths and music before we went live.
Yeah.
Do you want to do any foreshadowing?
Yeah. We'll keep. We won't have any spoiler alerts.
Okay. No spoilers. If you'd like to join in live, we are always keeping one eye on chat, which is appearing just underneath Maria. So chat on the stream, you've got me at the top, then Maria, then you, which you can join at slido.com/OOMC, which is also where you can let me know how was your day today. We've got a 5-star poll. So Maria, we do this every week. I guess we're tracking across the seasons how people's days were. We found out the obvious things about mocks and exams being bad for people's day. But how's your day been?
Oh, it's been absolute chaos. I had a trumpet lesson in London this morning, so I had to be on a train during rush hour, walked from Paddington to the centre of London, like to RCM, and then back again. And then once I got back here, I had half an hour before I had to sprint cycle to St Hugh's in North Oxford for a tutorial, and then come back for this. And I'm going on tour on Saturday with the Oxford University Orchestra, and I had to pack for that, and it's been a nightmare. But it's been a good day though. It's gone to plan so far, so we're doing well.
Tutorial cycle live stream sounds like a kind of triathlon for sort of nerdy triathlon, right? Okay. Chat's having a good day, which is nice. What would you say on a 5-star scale, Maria? I'm going to hold you to the format.
I'll keep it to a 4. I'm holding my reservations. I'm quite tired. I may or may not have been at a show after party last night as well, so it's been quite a day.
Okay, I'm going to do some quick shout outs. Hi to Shrish and Miles and Andre and Raya, who I can see in chat, and some anonymous people. One of the anonymous people has done a joke, which I won't read out, but not because it's bad, just because that's encouraging people to go and look at chat, where you can see a funny thing they said about oh god, I've really overhyped that. I'm trying to also work out with my other eye looking at the other side, how to turn off the poll. Okay, what are we doing? People have got questions for Maria. One person in chat wants to know what A-levels you did.
I did music history and German, but I also did a gap year. So I did a deferred entry and applied in like year 12 or year 13. Year 13, it'd be year 13. And then in my gap year, I did loads of extra music because I really wanted to focus on studying in year 12 and year 13. And then I wanted to spend my gap year doing all of the music at once. And it worked. So I ended up doing a lot. So that was good.
Music, history, German.
And yeah.
Okay.
It's also worth mentioning you don't have to do music A-level to do music at Oxford, because not all schools offer it, so they can't make it a requirement.
Oh, really? Okay.
Yeah.
Oh, that sounds a bit like maths and further maths maybe, but I don't know how it works. Is it the sort of thing where music A-level is helpful for? Is it similar or?
Music A-level is helpful for like writing essays about music and like some of the terminology. But I think what they say is if you don't do A-level music, do grade 8 theory instead, because then you still have like, you've shown musical knowledge and like skill and stuff like that. You also don't actually have to play an instrument, I don't think. You might have to play piano a bit, but
it's
otherwise...
not performance-based, is it? It's not a sort of...
No, I choose to do a lot of performance, but I know people who don't do any. So it's like, it's very adaptable to what you want to do.
So people are asking about gap years for maths, obviously, as well. So Maria described a gap year where you did lots of maths. No, wait, you described a gap year where you did lots of music. For maths, we allow people, we accept applications from people doing gap years. We like to see that they're planning lots of maths for their gap year. So maybe some sort of structured activities or something like that, something to keep doing maths.
Whenever people talk about gap years, I always say like make sure you have things planned. If you just say like, oh, I'll work it out nearer the time just goes. It goes so quickly, and then it'll get to like August and you're like, oh, I've done nothing. So I planned loads of things in advance that I wanted to do, and I said it, I think, in my personal statement to be like, I promise I have things like going on. I promise I have things on the like on the books. Um, I talk about this a lot because I also do like step up and outreach for state schools with college. So I sort of go into like Q&A mode whenever I have questions like this.
Miles wants to know about Baldur's Gate 3, which I'm not going to ask Maria about. It's quite a nerdy faculty. Let's just do that. What instruments do you play, Maria? You mentioned you've got orchestra. Obviously, you have orchestra tomorrow.
So I play trumpet, cello, piano, I sing, and I also conduct the University Wind Orchestra and do some composing as well. Yeah.
Very nice. And wind
We
orchestra.
actually did wind orchestra. We actually did a piece with the wind orchestra last term that had some really funky polyrhythms in it, like 5 against 4 and 5 against 3, which were quite difficult to explain coherently. But then once we got it, it sounded sick. It was so good.
There's some really good YouTube videos, maybe not this one, but there's some other good YouTube videos about polyrhythms of people demonstrating them in different ways. I might link to some. Okay, so I'll go first. I wanted to talk about maths of intervals and tuning. I know this thing about intervals. I know very little about intervals, but I've got this vague idea that if you have kind of two sound waves with different frequencies, so frequencies, what am I going to call the frequencies? I'm not really sure what people call frequencies. Do people call them omega or no?
I've never seen like the notation for it other than saying like this is the top note, this is the bottom note, or this is the fundamental and this is the overtone. That's all I've really heard.
Okay, these are the things measured in hertz or something.
Yes, so you say specific hertz and things like that, or you show the ratios.
Yeah, okay. So if it's like A and B, these are measured in hertz, or like how many oscillations per second you have. And they together, and this is a fact that I don't know where I learned this or what I'm even really saying, but they like sound good.
A and B, perhaps not. They're very close together, but like A and E, definitely.
Oh yeah, of course. I'm using these. Right. Okay. I'm using these as random variables. Shall I pick different letters like X?
Probably, yeah. If you're using random variables, it'll probably,
Okay.
probably be letters that aren't in.
You're right.
Aren't in the scale.
You music people, you're already using the capital letters, aren't you? Whoops.
Yeah.
Okay. You want this ratio or fraction, maybe?
We'd usually see them as ratios, but I have also seen them as fractions. So, in fact, in my research that I was doing for this, then you see both all the time. So, whichever's easiest.
So somehow this like sounds good if y over x, or the ratio is 2. That's got a name. That's called an octave. I don't really get it. I don't really know why that would sound good or what's going on there.
Well, it's because the way your brain processes sound and the way that your brain tries to interpret sound is that you tend to prefer like simple ratios between pitches. So it's why things like an octave or a perfectly tuned fifth or perfectly tuned major third sound good, because they're really resonant. And the reason that they're resonant is that you have the overtone series, which is where you have the fundamental note that is the a pure tone like a sine wave, for example, and then the overtone series is basically the hertz double each time, and they get weaker or stronger in different points throughout the overtone series. And when two notes sound together and the overtone series line up together and they're perfectly in tune, it's really bright and resonant, and you imagine like a round sound. Whereas if they clash a lot, and if the waves don't cancel each other out or anything like that, then your brain goes, it's too complicated, can't work it out, don't like it. That's basically like just the general premise.
Sure. We did some stuff about the wave equation, the mathematics of the wave equation a few weeks ago on Maths Club on this show. We drew pictures like this in the bottom left of different different wavelengths, which corresponds in some way through the wave speed to the frequency. There's a question about whether that's a learnt, is that a cultural thing, or is that a kind of physical thing about how your ear works, and maybe about the mathematics of how these waves interact? I'm not sure.
At least a large part of it is how your brain works and how the ear works. But then the way that those are then like perceived and interpreted is very cultural as well. So there are loads of like music traditions in, for example, Southeast Asia that have very different constructs around how they perceive or like how they interpret different ratios and pitches and intervals. And the risk is when you say like, oh, we prefer simple ratios because it's what the brain likes, then that's kind of you get into the danger zone of arguing that a type of music is better because it uses those intervals, which is what some music theorists have done to try and be like, European music is the best, and everyone goes, no, it's just a different type of music. Um, but the one thing that seems to be common is that almost every musical culture that has been studied, if not every one, has a perfect fifth in it, which is really interesting.
Oh, so
Yeah.
cultures, that's exciting then. The cultures across the world. I suppose we seem to have lots of languages have words for colours like black, white, and red. Maybe lots of cultures have also noticed that perfect fifths maybe is a thing that you can sometimes hear on strings or something if you set up some standing waves. Okay, what this made me think, or the kind of, I guess, constructive mathematics bit of my brain is like, well, what can you build with these, right? If I start with the number 1, I could find some things that sound nice together with that by going up by a factor of 2, or I could multiply by 3/2. But then maybe I could do it again, right? maybe I could say I could go up another octave. Oh, there was a draft of this where I thought maybe I could learn to sing octaves to demonstrate what octaves are, but I'm not backing myself to sing on this live stream.
Octaves are quite far apart. You'd be hard pushed to do more than 2.
Oh, okay. Right. Good tip. Okay, so there's a network I can make, right? If I go up by a factor of 2, and then go up by a factor of 3/2, then I've reached the same thing as if I'd gone up by a factor of 3, which sort of feels quite nice, that you go up by 2 and then 3/2. And that's also because multiplication is commutative. That's what would happen if I went up by a fifth and then an octave. So there's this kind of structure that I suppose I
Yes.
can build.
Yeah. So if you go up by the 3/2 first, and then again, then that's doing that prioritizing the fifth. Whereas if you go up by a factor of 2 first, then that's the octave. In fact, on my notes, I have a table of all the different intervals and their ratios and how they relate to one another. So an octave is 2 to 1, which means that for every one time that there's a cycle per second on one note, it happens twice in the note above it. So that's like,
Yeah.
I
Okay.
assume people know
Yeah.
how ratios
No,
work.
yeah.
And then the fifth is 3/2, and then the next one is 4/3. So it goes
4/3. Okay, 4/3.
Yeah.
Let's see if I can put that in my. Where am I going to get a 4/3? Maybe chat can help me out, right? So 4/3 seems. I'm interrupting Maria. I know. Sorry, Maria.
No, go ahead,
4/3's got some relevance, right? Is that going to appear on my diagram somewhere? Maybe chat can help out. Neutrino, we are using just intonation at the moment. I am currently obsessed with exact ratios. Somebody else asked, maybe it was Neutrino actually asked if you work on microtones.
Yeah, so that's a whole different conversation, and like a really, really interesting one at that, because when you get to microtonal music from other cultures, it's like, to them those aren't microtones, those are just the tones that you use, whereas to us it's like, oh, that's like a note between notes, and it's like, no, it's just differently tuned. So microtones can be the space between notes, or they can be differently tuned notes. So it massively depends on context. But yeah, I mean, my dad wrote a piece for 13-piece string orchestra and solo viola that was about like Syrian refugees and their experience of like, it's called Music of Exile, and it was played by this amazing viola player called Raghad, who had like escaped from Syria, and she taught us how to play this particular scale that is like to do with loss and longing, and it had microtones in it, and it's like, it was really like tense and like as a sound. And so yeah, I've worked with microtones in that way before. Like with string instruments you can do it a lot because it's just like You could just slide up and down all day and see what happens. But
So microtones are notes that differ by just a little bit, or is it a,
yes.
a system of? Okay, yeah, okay. So
But that's also to do with like equal temperament, and then we get into a whole other conversation again.
yeah, I hope we get to some sort of idea about equal temperament. As always, if we don't cover something in the live stream, but we wanted to tell you about it, it usually ends up in the further reading notes, which we put on the website afterwards. Who's in chat? Anonymous has told me that 4/3 won't appear on this diagram because, because I'm going to have only whole numbers or things divided by 2, but they haven't allowed for my willingness to go in the opposite direction. So going up by 3/2 is a perfect fifth. I said I was starting at the note like with, I'm not sure if I mean 1 hertz or just like relative to this bass note. But I could also go down by a perfect fifth. So I guess my diagram extends this way as well.
Yeah. The way you tend to go down by a perfect fifth is that you do the inversion. So rather than 3/2, you do 2/3.
Sure.
And if you're multiplying ratios.
Yeah, I guess that's in this sequence. If I'm reading right to left, it goes, multiple of 2/3 each time. Okay. So 2/3 belongs kind of over here on the diagram. And then I guess this is over here. Here is where 4/3 lives. So then you go up by 3/2 to get back to 2. And really my diagram should go over this way as well and expand outwards to allow me to go up by a fifth and down by a fifth. Okay. A perfect fifth is a musical interval. I'm looking around me for an example of a perfect fifth. I've got a music student.
I have a wonderful example of some perfect fifths, which is my cello right here.
Right.
So cellos are tuned in fifths, and they have to be perfect, otherwise it doesn't resonate. So I'm just going to put the spike up so I can actually play it. Probably a good idea. But a perfect fifth sounds a bit like this. It's not too perfect, but so it's like really, really open. You probably can't hear it over the microphone, but this is a G, and that's a D. They're a fifth apart. And then because they're really in tune with each other and they're resonating really well, even though I'm only playing 2 strings, it makes the top string vibrate, and so you can just about hear it. So you hear the A above. I don't think you'd be able to hear it over the microphone.
Oh wow!
But yeah, when you play,
there's some resonance on the other strings as well. There's a fact about cellos, right? That you have the other strings available. That's really cool,
you get it with all string instruments. That if you play something really in tune on the lower strings, then because the overtones are vibrating, even if you can't hear them explicitly, but they are there, they make the string that is like equivalent to that overtone vibrate. And that's how you can tell if something is in tune, because the string vibrates anyway.
That's really good. So it's sort of a superposition of 2 notes that just sort of, I'll be biased, sounds good when you play them together, or sound like they go together. They differ their frequencies differ by a multiple of 1.5, 3/2. And so you can do a perfect fifth because it's a fact about ratios. You can do one starting at any note you like, and then go up by just multiplying the frequency. Whether or not your cello can support any frequency I throw at you, or whether you can support going up by 3/2.
I'd have to start retuning the strings, and that would take far too long.
Can you is it fretless or fretted?
Yes, so cellos don't have frets, and neither do violins or violas. Like all of the bowed string instruments in Western music don't have frets. So, which is why you can be a bit freer with microtones, because there's nothing stopping you from going in between the notes.
Okay. So this diagram that I've been working on, which maybe confuse people in chat, is me just messing around with what you can build by going up and down fifths and octaves. Oh my goodness. Hi Burrito Man. That's a deep cut. Right. Something fun happens if you keep going up in perfect fifths, which people who do music exams maybe know where I'm going with this. Maria's smiling. I've got a table though for the mathematicians like me who didn't do this kind of exam. I've got a table of what happens if you keep going up. So if you want to forget about the diagram and just look at powers of 3/2, here's me working out some powers of 3/2. I've got the numerator and the denominator here, where I'm doing powers of 3 and powers of 2, and in pink I've got the ratio. So this is the thing that starts off at 1.5, and then if I go up with it by another 5, that's a bit larger than going up by an octave. I suppose comparing that to an octave would be, this is like an octave higher. So it's like a factor of 2 larger. Higher, so it's an octave higher than, I'm struggling for this, octave higher than 9 over 8. It's twice as big as 9 over 8. 9 over 4 is twice as big as 9 over 8. Well, to the maths club. Is 9 over 8 a special thing? Is that a thing?
Well, it's more that you say it's bigger than an octave, and of course that's right. But so if you stack up in fifths, the great thing about having 4 strings. So that's our fundamental, and that's the next fifth, and we've got a fifth above that. That's more than an octave. If you wanted to do the octave, then you'd have to go down 1. So that's the top note. Then you go down 1, and then that's 1 to 2. But you have to use your fingers for that, because it's not with the natural fifths of the strings.
It's always like, having the cello is brilliant, but it's almost like anything you play on the cello sounds good at the moment.
It's a very resonant instrument. It has a great sound. I'm a big fan.
Okay. Yeah, okay. So, for me, the exciting thing happens when you get to, what do I want to point at? When you get to this line, this ratio. Because I've been doing powers of 3 and powers of 2, and I guess kind of obviously you're never going to get a whole number out of this, and you're not going to get a power of 2 out of this, because it's never the case that 3 to the m is equal to 2 to the n for any meaningful values of m and n. This one's odd and that one's even, but this is really close. This is really close to 128, which is a number that I get by going in a completely different direction on my diagram. So if I go octaves, I get to 128 after, 2, 4, 8, 16, 30, 64, 7 octaves in that direction. And if I do perfect fifths, 12 of them, I get to almost the same note after 12 of them? Is that a thing?
Yes. So in the Western European music system that we use, that we have 12 notes in a scale, like C, C sharp, D, D sharp, blah blah blah, until you get to C again, which is also how you taught me that, how I could understand modulo numbers, because that's how octaves work. And I was like, you know what, you're so right, how did I not think of that? But yeah, so it makes sense by the time you get to 12, you'd expect it to be very close to being in octaves, because of course, well, you can go up in fifths, you can also go up in octaves, and this is why using just intonation, which is using the simple ratios, doesn't work practically, because you can get to the same note, or almost the same note, in more than one way. So if you keep stacking octaves to get to the same pitch on the piano, for example, although piano is a bad example, but on a string instrument, for example, then you'll get to the C 7 octaves above the first one. Whereas if you do it in fifths, you'll still get to that C, but if you're tuning them perfectly, then they're not going to be right. They don't equal each other, which then becomes very impractical if you're trying to do a long piece of music or have a big ensemble. If you try to tune them justly, then they get slightly more out of tune each time. And there have been loads of different ways people have tried to solve this, from mean tone temperament is another one, well temperament is another thing, so they're all different names. I know they've got weird names, and they're all trying to work out how to solve this problem. And I think this is the right point to mention a fact that I told James earlier, which I think you quite enjoyed, which is that when you get to that top fifth, so that sort of 11th, from the 11th to the 12th note, it's so out of tune that the beats where the frequencies don't match is so bad, it sounds like it's howling, and so it's called a wolf note.
Wait,
and you get them on string instruments, because string instruments, if they're tuned justly, and then you try and play those notes, then they make a really weird sound. I think I can try and demonstrate it on my cello. I can give it a go.
So to check I understand what you're going to do, you're going to try and jump from... Wait, do you have to go up 11 fifths? No, I'll just lead it. No,
there's actually on the cello, there's a very specific note on one of the strings that it's never in tune, and I don't know exactly why, but I think it's to do with that. But if I try and, well, you can't quite hear it, but it's basically like it's a weird interval above one of the strings, and it starts cracking if you start playing it too loudly, and that's a wolf note because the string just can't handle it, and it's like it just doesn't vibrate properly. Some people try to fix it by having a little device on their string that stops it from vibrating like that.
Is that a factor about just one string, or is it the cello resonating other strings again?
I think it's almost the opposite, that it can't resonate the other strings, so it sort of collapses onto itself. Because string instruments rely on being able to make the other strings vibrate in one way or another. And that's also why different instruments sound the way they do and why they have different timbre, or like the colour of the sound. And it's to do with which overtones they emphasise.
Right. So I suppose it would be quite nice if this... right, we've discovered why Western music's kind of got 12 notes, I think. That if you give these names, they're not quite in the right order because they're going up by quite a big jump each time. So it actually names them. I guess you drop them by factors of. You try and drop them down to be within the same octave range, and then label them A, B, C. No, you label them with the semitones, right? I used to know this sort of thing.
It's like C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, or people usually say B flat, B, and then C. And we can thank Pythagoras for that. But as you can for many things, really. But yeah, so that's... I can't remember if it was that they were tuning it by semitones first or by fifths, but yes, that is why we have 12 notes, because by the time you get to that one, they're so nearly the same so that you can basically say they're the same note, and then you can crush them back down again to be within an octave, rather than being spanned over fifths. In fact, in music, we have the circle of fifths, which is where the notes are grouped in fifths, and that's to do with key signatures and how bright or how dark something is.
See, but if you actually go up, if you look at the circle of fifths, it kind of implies that you go up 12 fifths. You should get back to the same letter note name, and we're pretending that that's a certain number of octaves above. But of course, 3/2 to the power of whatever you like is never really going to be a power of 2. I saw in chat Andre and Imo are talking about whether this happens again, whether you could just sort of delay the problem and wait, and I think you can.
That is exactly what they tried to do. They just tried to push that wolf note further and further up the instruments by tuning them differently, especially when they tried to first make pianos and to an extent organs as well, but mostly pianos, that they were just trying to hide that really out of tune fifth further and further up the instrument. But then, when we're talking about it here, it's like it's almost the same, but not quite. You could almost ignore it. By the time you delay it further, it gets more and more out of tune to the point that it's not even the same interval anymore. So that's why they had to kind of spread it out a bit more and make it so that everything's a little bit out of tune, but it's close enough that you can almost you can allow it.
Because of course these funky musicians, if you give them all the keys, they're going to try jumping around between all sorts of combinations, and you kind of can't make all of those sound good. That's annoying.
Yeah, that's the thing with just intonation, is that it works beautifully, especially on voices or string instruments, as long as you don't change key or do anything really funky, because then that's when you have to tune it by different ratios, and then and like have funkier interval ratios between them. And that's also why if you ever sing in a choir, or you've heard a choir sing without any accompaniment, they gradually get sharper or flatter because they're tuning to each other perfectly. But because they're doing that, the pitch doesn't stay consistent. There's a really good video essay I'd recommend for this by Adam Neely called Benedetti's Puzzle, or the Syntonic Comma, or alternatively, the Cosmic Joke, which is the idea that music can never be perfectly, mathematically, consistently in tune. Because if you try to do it, then if the maths is right, the music will be wrong, and if the music is right, then the maths will look horrible. So you kind of have to decide which one you prefer.
Okay, brilliant. I've got a maths related thing. I'm not certain if this is totally relevant, but there's a really nice math result that I'm going to take 5-10 minutes just to get to this maths thing. that I read about a couple of months ago, and I've been so excited to do it on the stream. So we're gonna do this now. I'm not sure it's really got musical significance, but we'll find out. Okay, chat. This is the task for you. We've seen that we're making numbers out of powers of 2 and 3, and because we can go up and down, I'm interested in just any like combinations of powers of 2 and 3. They let you build numbers like 6, we've already seen. But my challenge is to find a pair of consecutive numbers as close as together as they could be, which each just have 2 and or 3 as their prime factors. So that's my challenge to chat. Maria, I guess you can join in as well if you like.
This is ringing a bell from when I was doing GCSE maths, and I'm not going to embarrass myself, but I will be quietly working things out in my head.
Okay. Chat says the chat is mostly talking about H as a musical note, and one person says inside you there are 2 wolves. One is a horrific cello noise, the other just likes maths.
I want that on a t-shirt.
It meets the bar. Well done, Burrito Man. People in chat are excited about Adam Neely. There's also a shout out to Jacob Collier.
Yes, Jacob Collier! Very big fan.
People in chat have spotted that 2 and 3 are themselves consecutive numbers that don't have any other weird prime factors around. So that's a good start. Oh, look at this. Chat's off and away. And I've now measured exactly how much chat lag is. I've also spotted 8 and 9. Good job, chat. Which we saw before. We saw it in the table as I came up as I took an octave down from 9 over 4 or something. Any more? So there are some other ones. Yeah, so chat has. I'm giving chat a moment to catch up. Chat's now worked out that 3 and 4 count. If I make this, and 15, 16's appeared in chat as well, which is close, but actually an answer to my next question because of the 5. So you're not wrong. You're just from the future answering the next one. So there's also. Oh wait, yeah, I haven't really set this up very well because I would count. I think. What do I want to put here? And or slash nor maybe. I'd kind of like to permit 1, 2. It's not very important to me that we include 1, 2. I just feel sorry for 1 being left out without any prime factors, I guess. I'm not going to get away with that. Sorry, I should have put nor on the board as well. And surprising maths fact, that's it. So those are the only pairs. You might expect that there'll be some more like really huge ones, like an enormous power of 2, like 128, that might be right next to a power of 3, and that'd be quite good because that would give us some combination of fifths and octaves that's just extraordinarily accurate. But that never happens. It's not game over. We can try. We can get things like 128 being quite close to 128 point whatever. But that's it. There's only 4. And intervals of this format, of like consecutive numbers, tend to have names in music. So I thought we'd teach them the names. Have we mentioned all of these already? I'm not sure.
I don't know, but I'm trying to think. Yeah, there are some funky ones. There's I've got different ratios of consecutive numbers, but I'm not sure if that's exactly what you mean.
But maybe with other prime factors. So Pythagoras has only got 2s and 3s because Pythagoras can only do octaves and perfect fifths. I guess Pythagoras can construct, this is called Pythagorean triple, right? Can construct a 4th. I've just looked at my notes which say this is a 4th. Please do correct me, music students in chat or on stream. And then Wikipedia told me that one's called a major tone, which I don't really believe, but whatever.
Oh yeah, I see what they're trying to say. Yeah, it's like they've combined 2 different sets of terminology that it's either a whole tone or a major second, and they've decided to call it a major tone.
I may have copied it off Wikipedia wrong.
That's fine.
Anonymous asked for a proof, and Herb says it's surprising. Oh, Anonymous. No, I've been saying fifths. I just mean a ratio of 3/2 on the notes. Maria played one on a cello. It sounds like it means 5 notes apart, which we haven't addressed, right?
No, so yeah,
What's 5 about it?
So fifths are not 5 semitones apart
That's annoying.
because we don't really. I know. We don't really think of scales in terms of semitones, and the names for the intervals come from scales. Because if you just think of intervals in terms of scales, then the only time that you'd be able to use all the notes would be a chromatic scale, which we don't use to make chords in like typical harmony, because then you've got too many notes to hand, and so it's like which one's the most important. So instead we have 7 note scales, particularly like the major scale, the multiple different minor scales, and then you get some really cool funky ones, but we're not going to get into those just yet.
We're getting there.
We'll get there. We'll get there eventually.
We're getting there. Jordan's
yeah,
late. Is this music? Yep. I've got Maria. Maria's a music student. We're doing mathsy music.
But yeah, so they're called fifths because they are 5 scale steps apart. So for example, C and G in a C major scale is C, D, E, F, G. So that's why it's 5 notes apart.
And I think scales more of a cultural thing than.
Yes, very much
okay,
so.
Right.
So like Western European classical music tends to use like the 12 semitones, and then we have very specifically major scale, minor scales, and then you maybe have some ones like the whole tone scale, which is where all the steps are equally the same amount apart. And it's the whole tone because it's the whole tone, as in like it's rather than a semitone, it's 2 semitones. It's the whole thing. And then you get some other things like the altered scale, the octatonic scale, but those are slightly more advanced. Whereas in other cultures, for example, in Indian classical music, you have like hundreds of different types of scale. They all have really like important, significant names and even like associations. So there are some that you can only play at certain times of day, or that have very specific associations with different times of year and different seasons. And so they're very different.
And just to link back to something before to help an anonymous person in chat, before I said 12 fifths makes 7 octaves because it works out as being pretty close to 128, which is 2 to the power of 7. So a fifth is quite a large interval, really. It takes you up by an entire factor of 3 over 2. Sounds really
It's
good.
over half the octave. Yeah.
Right. I was going to say on a logarithmic scale, but then I lost all confidence and just kept that to myself. Another game with just factors that just 2, 3, and 5 as their prime factors. And while chat thinks of some examples, yes, thank you, Maria. There we go. 1, 2. I feel like you maybe had some of these. Wait, you're giving me a whole sequence of numbers because you've noticed that small numbers all work for this because they don't have any weird factors. Then 7 ruins the party a little bit. I'll give you a little bit of a flavour of the proof, if you like. The idea is to consider looking for numbers of the form s plus 1 with only a few factors, with only a few prime factors. A few different prime factors, I suppose. Prime factors from our small set of 2, 3, and 5. If you can find numbers of that form, then you're done, because S must be of that form as well, and then you've got S plus 1 as well. Chat are giving me so many of these. This is brilliant. 9, 10, and they've even found 25 over 24, which Wikipedia told me is called an augmented unison, which I really didn't believe. Maria, have you ever heard of an augmented unison?
That's just called being out of tune at that point.
So close to 1. These are sort of bad because they're so close to 1 that it sounds like you're playing the note and a slightly mistuned note at the same time. So, depending on your culture, that's either a normal part of your music or slightly out of tune.
Yeah.
Okay, there's a way to convert these to just continue my sketch proof. Convert, which I'm not showing you the details, to solutions of, and it is so nice, but not right now, solutions of x squared minus dy squared equals 1 for d, where so d has just a few prime factors, Wow, this pen is really not helping me here. Just a few prime factors, and is square free. Doesn't have any, and none of them are repeated. So it's a multiple of 2 but not 4. It's maybe it's a multiple of 3 but not 9. Maybe it's a multiple of 5 but not 25. That's sometimes called square free. That's just a few cases to check. So then you solve those equations, which is a whole thing. Separate live streams maybe on solving equations like this, and you generate some solutions. After a while, those solutions have very large prime factors, so they don't lie in this interesting set. So there's only a few things to check for you to work out all of these. John in chat has found 80,81, brilliant, which is the largest. And I think we've actually got we got 15, 16? That was one that's also before. We've now got all of the, these are called 5 limits. These are called super perfect intervals from 5 limit tuning, I think. Did I get away with that?
Yeah, they're looking familiar, it's all good.
Okay, so this is 5 limit tuning. I don't know if it has any other names, but sort of.
Yeah, I think I hesitate to say anything else. I've just got the list of intervals, which is a website that has a lot of different ratios and all the different names for all of the different intervals you could possibly have. But yeah, 5 limit tuning is the standard used for for just intonation.
Yeah, so Aya in chat has put an interesting claim about a semitone being the 12th root of 2. So if you try and split up 2 into 12 equally spaced ratio jumps, then you should use the 12th root of 2. And that's what equal temperament is, right?
Yes. So equal temperament is the idea that all of the notes are the exact same amount apart. So they're all 100 cents apart, which is another different measuring system, which is used specifically for equal temperament to show that they're all the same amount apart, and to differentiate between equal temperament and just intonation. But yeah, so that's why on a piano everything works in every key, because all of the ratios are basically the same, because all the notes are the same amount apart.
So everything is slightly off. The thing that could have been a perfect fifth, 3/2, is actually some weird irrational number that's kind of near 3/2. So kind of everything's wrong. Which is
that was the trade-off.
Pythagoras would throw you off a boat for that. But that's just what they were like. Anyway, I'm not going to list them all out, but if you play this game for 7 limit tuning, there's more of them. So this is more work. There are 23 pairs like this, if you count 1 as being a number that you can use. And the largest is 4,374, 4,375, which has got a name because this is 7 limit tuning, which is maybe a thing.
Yes. When I first saw this, I was like, I don't think I've ever come across septimal tuning. I don't know where I would ever hear it. And then it turns out that, I don't know exactly why, but if you've ever heard a barbershop quartet, so a very specific style of singing, and it has a very specific feel to it. Everything feels very close and very an intimate sound. And barbershop tuning is something people are known for, as in when they do competitions for this kind of singing, the thing they pay the most attention to is how you tune together. And in barbershop singing, you get a lot of the minor 7th interval, because that's part of the harmony that they use. It's part of that style. And it turns out the 7th that they use, that is so typical and such a recognizable sound of barbershop, is actually septimal tuning, and because it's a slightly flatter 7th, I think, than the 5 limit tuning, minor 7th that you'd get. There's a whole Wikipedia page about it, and it compares the two. So you have a minor 7th in 5 limit tuning, followed by a minor 7th in septimal tuning, and they're recognizably different, which is I found really interesting. I remember reading about that when I was becoming a tuning nerd, when I was writing my personal statement, And I remember being very excited about the fact that I was like, oh my god, this thing, it's there, it's a maths thing. And I was like, I didn't expect it to be there at all. I'd never noticed it. And then I heard it and I was like, oh my god. So yeah, it is actually much more common than you'd think.
That's brilliant. I'm sorry to ruin it one earlier, Anonymous. It's 410, sorry, thing in chat. 41023. The sequences in the Encyclopedia of Sequences. I'll put a link in further reading. It's a really weird sequence. You get a lot of these, and the best method we've got at the moment is following the proof that Sturmer and Lerma worked on at different times. You just get this system of equations to solve. Like you get a bunch of these things. There's a technique for solving them that gives you things that might be solutions, but you have to check manually whether the things that you get out actually belong on this list or not. So it's like checking your answers at the end of the question. You have to check that they fit. So it's like actual work to calculate them. Cool, right. Okay, 35, 36. Yep, that's a good one. I love the way that this sort of mathematics of looking at these particular intervals, consecutive numbers, or the ratio between consecutive numbers, has some maths. It's quite difficult Pell's equation kind of maths. But also, once you've got the answers out, they've almost all got names already because musicians were already aware of them. So I just really like that crossover. I've run longer than I said I would, Maria. Sorry. Do you want to switch to your thing?
Yeah, so we've talked a lot about the tuning and stuff, and that was what when we were initially planning doing this, what we thought would be interesting to talk about. But then this term in my course, we've been doing music analysis. It's trying to work out harmonic structure and how chords work and things like that. And then our tutor was like, so you're going to have to do some DFT analysis. And I was like, oh, I've never heard of this. And then I was reading about it and having to learn it, and I was like, this is really complicated. I don't know what's happening here. And then I mentioned it to a friend of mine who does maths and computer science, and I was like, oh, God, this thing called discrete Fourier transformations. And he went, oh my gosh, you're doing discrete Fourier transformations. And I was like, yeah, what is this? So my understanding of it is very specifically to do with music and harmony, but I tried to read about what they are in the mathematical context, and I will be completely honest and say that it brought tears to my eyes because I hadn't seen that much maths in a very long time. So if we could have the maths definition of DFT and what it is, how it works, and then I can say how we use it in music.
So I'll do a really brief version because I've already talked too much, but it's a sort of signal analysis to take a complicated signal and to isolate the kind of frequencies that make up that signal. Like taking, like when you mix together the colours of paint, you could maybe have a kind of paint expert who would look at that painting with the really vibrant colours in it and say, aha, that's being made with quite a lot of yellow, a little bit of red, and surprisingly a smidgen of blue. That kind of analysis of breaking it down into the kind of primary components. For paint, that's different primary paint colours, I guess. It's perhaps surprising that you can do that on waveforms. You can do that on music or voice or speech or any signal that you're processing. And discrete Fourier transform is a discretized version of that, which I know less about, but it's a way of breaking down that signal into its kind of component parts, which might contain interesting information for you.
Yeah, and that now makes a lot of sense because when we use it in music, it's when we have, let's say, I talked about major scales earlier, and sort of when you hear a major scale, you'll recognize it immediately. Even if you don't think you know music theory, you will know what a major scale sounds like. And then when you look at the notes, it's you can even look at those notes and think, I know that's a major scale. However, when you get to slightly more recent harmony and composition within the last 150 years or so, maybe 200 years, then composers started to be a bit cheeky and would use those notes, but maybe add some extra ones in that didn't make sense, and they seemed to have no relation to what was happening before. And when you're trying to analyze that and understand it, it's well, how do I describe this? Where are we? If I'm looking at the piano, or if I'm looking at a circle of fifths, and I'm looking at this sort of bag of notes in front of me, where are we? What's going on? So, do we have the vector diagram thing?
Coordinated as, there we go.
So this is made by music theorists who also does, like, she was also a mathematician, terrifyingly intelligent person. It's also worth mentioning this field of musical study is so new that there are only 2 people in the UK who teach it, and like 5 people in the US. This is incredibly niche, and I'm very, very lucky that one of my lecturers is like one of the sort of like forefront people doing DFTs in music. Um, so before I mentioned that we have the 12 notes in the octave, and I was using letter names for them. When we get to like more recent music, it gets quite complicated to use the note names still because often they contradict each other. So I can't remember which theorist it was, but someone came up with the idea of what if we just number them from 0 to 11.
Okay.
So 0 is always equal to C. 1 is always equal to C sharp or D flat. They become the same note, whereas even if in the context they're not. So the pitch class 0 is another word for C. The reason why we say pitch class rather than the note is because note and pitch aren't the same thing. So note is the like the name of it, whereas pitch is the sound, which seems like a strange distinction to have, but you need it when you're talking about if like all the notes of the music are really far spread out on the piano and sometimes they repeat and sometimes they don't, then you have to say that this C is equal to this C, even though they're 4 octaves apart. So to make the analysis simpler, you condense them down to the same pitch class.
So it's a sort of quotient. You're kind of taking the piano, which is linear, like the number line, and sort of rolling it up so that a C over here and a C over there and a C all the way over there are going to count the same in your analysis, which is the same sort of rolling up that you do for modular arithmetic, which is why we keep coming back to that, I suppose. This I can already see a kind of circular diagram on the right for, I guess, this thing about as you go up the scale, the letter names come back again, right? You go A to G, and then there's A again, notwithstanding H.
But to demonstrate what this tells us, so basically, as you'll see, the magnitudes and the vector show us where we are in however we're choosing to organize the notes. So if you go to Fourier component and you press F5.
F5. Whoa, okay.
Yeah.
Something happened over here with things whizzing around. They're now, all the circles are now coloured in purple. Okay, so we've got our octave set up.
The way so what's happening on that circle is that we're going up in fifths, starting with 0 on the right. And it's basically,
okay.
If you've ever seen a circle of fifths, then usually C is at the top, but this particular theorist decided to put C on the right.
Yeah,
not entirely sure why.
Yeah, 1 is on the arcane diagram, isn't it? So we go around, so I see, so 0 is here, and then it counts around however many that is to get to 1, and then it counts around to get to 2, and then same amount around to get to 3, and then 4, and then 5, 6. Okay, right, yeah, I can sort of see that it's doing steps up, which you say corresponds to going up in a circle of fifths or something.
So 0 is C, and the next one up is G, which is 7, I think. Oh, so I think going the other way around.
Sorry, that way.
Yeah, so that's 7, and then we go up to D, and that's 2 because it's 2 pitch classes above the 0. So that's that you have to kind of fill that in your head. If you're a music student looking at this going, oh my god, what am I looking at? Then it's just a circle of fifths but with numbers rather than letters.
Oh yeah, it's my diagram again, but wrapped around so that the numbers appear between. Okay, right, okay.
Yeah. Then if you go on magnitude and you put the number 1, just 1, nothing else, in pitch class 0, pitch class 2.
Oh, it's doing something. It's drawing me some vectors.
Pitch class 4. Pitch class 5.
Nice.
Pitch class 7.
Yep.
Pitch class 9. And pitch class 11, and then press calculate.
Okay, so you've given me some little vectors, and I think it's going to try and add them together. Nice. Okay.
Yeah. So that's basically telling us that we are so I think the highest magnitude that we can get on this diagram is that, and this is telling us that we are completely diatonically, as in with no ambiguous notes, no funky things. We are completely in C major. It's not pointing to C, and that is because for this to work, the scale that it uses has to be symmetrical. The major scale is not symmetrical. So instead we use a mode. So it's basically the major scale, but starting on a different note. So it's the notes of C major, but starting on D.
But you're telling me because that green arrow for the resultant vector is pointing directly at one of the purple blobs.
Yes.
That means it's directly, okay, it's not pointing at 0, but it's pointing at one of them. So now, okay.
It's pointing at the number 2 because 2 is D, and D
Right.
Dorian, which is the mode that is completely symmetrical, is basically an indicator of C major. This is quite complicated, even if you do know music theory, so don't worry if you're getting a bit lost. But because you have to use a symmetrical scale for the vectors to make sense, then it points to the Dorian of the major mode rather than the major mode itself.
I feel like we could do a separate live stream on modes and Lydian and modes and tunings. So I'm just going to grin. But so I see there's a vector thing happening that's important for your music research, and the fact that it points in the direction of one of these equally spaced purple blobs sounds like something that the math students in chat could join in with, but also has some meaning for you analysing what mode this music is in.
And then, so this is where it gets interesting. It's interesting already. Okay. But sometimes when you get very dissonant music, so music that doesn't use major or minor scales, then you have loads of notes together. And if, for example, let's add to the magnitudes on the side. If you keep them as they are, but then add pitch class 1.
Yep, another 1 in there.
Pitch class 10.
Oh, okay.
And I'm just going to go completely randomly. And pitch class, let's say 6. Let's do that for fun.
Okay, so I'm going to add in some extra random vectors.
And now press calculate. Ugh. So the magnitude is much smaller because we are nowhere near as close to something diatonic. This is not a normal scale. It's not typically major or minor. It's a bit crunchy, and it's also not pointing to one of the smaller circles because it's not so close to like any of the other keys either. So
is the application here that when you're putting in ones here, you're imagining maybe there's a tune or something, or is this lots of notes at once, or is this a sequence of notes that you're analysing? Or?
When you're doing this kind of analysis, you have to condense everything down. So this could be 2 chords on top of each other, or it could be a melody that you're deciding to analyse all at once. So if you want to say, what key is this melody in? Because it's really strange and it does all sorts of like funky, sinewy things and I can't work it out, then you do it like that. Okay. However, when we're trying to analyse this kind of music and then the Fourier component 5 is giving us quite small magnitudes, then old music theorists would say, well, that clearly means it doesn't have any kind of organisation or any kind of tonality. We can't call it anything. However, if you change the Fourier component, then it changes how the notes are organised and uses a different kind of modular number. So just put any of them in. I don't know what it might be.
I'm going to go F3, and that's spun everything around. And now I've got like, oh my goodness. So F3, because 3 is, oh my goodness, I guess 3 is not co-prime with 12. So this diagram's already really weird.
Indeed.
And then the resultant vector is, well, still a bit of a mess. It's still over here.
But so the way that, so F3 is basically that rather than the notes being organised by fifths, they are organised by augmented triads.
Oh gosh. Okay.
So that's what all those numbers mean. If you played those notes with corresponding pitches on a piano, then they would be an augmented triad, and that's how they're organised instead. So when I was writing an essay about a piece recently that used all sorts of funky notes, I was like, well, it doesn't make sense to use the circle of fifths for this because it's too dissonant. And then I used instead a different Fourier component, and then suddenly the magnitude was massive because it was just organised differently. I think it was organised by diminished sevenths, so like 4-note chords organised by equidistant minor thirds. In fact, I've got my essay up here, so I can read out the pitch classes that I had to use.
Okay.
Let's see. What was I? I need to go through all
So
my
I
pitch
think if I
classes
learned
again.
this, I think this is up my street while you're finding it, because I quite like the idea of replacing all of the stuff like learning C sharp and D flat, and just replacing those with numbers 0 to 11 and some mod 12 going on. And I like the idea that maybe these Fourier components, or whether you're tuning with fifths or something else. So this is a system on the board that doesn't use the circle of fifths, because it uses a different fundamental unit. I think I probably appreciate that in my musical understanding. Maybe I should do a musical degree.
Yeah. Oh, I'm trying to find.
Anonymous
Okay.
was asking about electrical engineering, and I think the music degree doesn't go that
No.
in that direction.
There is an electronic music module that you can take, but I don't know how much it does electrical engineering. I'm trying to find a good example that shows this, but I can just show instead. I'll make up an example.
Okay.
If you put in F6 as the Fourier component.
Oh, that's really weird.
Yeah, that's
F6
really
is
strange.
half of 12. Right. Okay.
And
So you
then
treat things. If you
then
only believe in a half step, then okay, yeah, sure. Okay, sorry, carry on.
then in the pitch class, like 0, 1, 3, if you just do all the odd numbers.
Okay. Yeah, okay, they're going to point in. Okay. I don't know what odd number is, I'm so sorry.
So as
numbers.
so it's just pitch class 0,
Yeah, okay.
just pitch class 3, 5, and then calculate.
Okay, and they're all pointing in that direction, so the resultant is over in that direction as well.
So the result of that is a whole tone scale starting on C. And you see that's a really strong magnitude, and we can very clearly see that it is that. Now if you change that to F5 again.
Ugh. Oh no, hang on.
Yeah.
So
It
now
doesn't
it's
even give a magnitude, because they're equidistant, which means that it doesn't point to anything specifically in a circle of fifths key. Whereas if you were deciding to organize something by whole tone scales, you can see exactly which whole tone scale it is.
I see. So you've got kind of different. These are like different filters on your glasses. Like I used to get.
Yeah,
these
that's exactly
I used
it.
to get these rave glasses that were horizontal lines, so you couldn't see things. Anyway, never mind. You've got different filters on the world. If you only look for perfect fifths, maybe you see there's nothing in this pattern of notes. But I see you're telling me that if I change my worldview and don't use the circle of fifths, then well, that one was also 0. Then he says, changing it back correctly, then you can say, actually, I recognise this. It matches up. The analyzer thing recognises this as strongly being odd numbers.
It's very interesting. I really enjoyed doing things like this. It sort of scratches my brain in a very satisfying way. And also because a lot of the music I like to listen to uses this kind of more interesting harmony, well, in my opinion, more interesting. The specific piece, if anyone is interested, was the Peter Warlock Capriole Suite, and it was specifically the 6th movement, so the very last section in it, that seems really normal at the beginning. Like it sounds like a folk tune, it's very simple. And then he just goes insane for the last third of it and starts genuinely just key smashing. And I was like, what is this? I need to work this out.
I love the idea.
And it turns out there is.
Oh, sorry.
It turns out there is logic to the madness. And I was like, this is so cool. There was a whole bit that it stopped being. So most of Western harmony is organized in thirds. It's called tertiary harmony. But then you can then try to organize things by fourths instead and use quartal harmony, which has a really interesting, like very different vibe to it, because the fourth to Western ears sounds very dark and it sounds very closed. So having everything stacked in fourths makes it feel very, like, it has a very different feel to it. And also, fourths don't occur naturally in the harmonic series in relation to the fundamental. Like, you get the distance of a fourth between notes, but because everything has to be in relation to the fundamental, fourths don't work. You get an augmented fourth so or a raised fourth, but you don't get a fourth itself. This is in the musical harmonic series. It might be different mathematically, but in terms of instruments and notes, you don't get perfect fourths unless you do the inverse. And
Right.
I mean, some other time I'd love to talk to you about the undertone series. There's so much debate as to whether it actually exists or not, but I'm obsessed. It's so
Oh, that sounds
interesting.
great. Okay, I think we're at time though. I'm afraid. People in chat are asking if you have a favourite chord and can you drop a playlist. So
I would so drop a playlist, genuinely. I can absolutely do that, and then we can put it on extended reading because in fact, I did make a playlist for other people in my A level music class, which I don't think any of them watched, but I liked doing it. So. But yeah, and
okay,
my favorite chord is a minor chord with a major seven in it. It's so crunchy and it has so much like tension in it, but also when you then resolve it to a sweet major chord, then it sounds even more like oh. And also I have synesthesia, so I see colors when I hear music. Um, and I have really strong associations with particular keys and colors. So my favorite keys are also my favorite color, which is just a little fun fact.
bro. I think someone is trying to rickroll you probably because they've asked what music theory does this use, and it's an anonymous looking YouTube link. So we'll save that one for later. Great. Okay. Maria, thank you so much for coming on Oxford Online Maths Club. It's the first time we've had a non-mathematician, non-computer scientist on the stream, and I think it's been lovely.
It's been an absolute pleasure. If you have me back sometime, I'd be so happy to join.
um, Thank you so much for coming on the stream. Is there anything you want to shout out at the end, or any? Oh, I don't know.
Always be curious with your music. Always listen to things that you think you might not like, and then you'll end up finding your new favorite things easier.
That's adorable. Brilliant. I thought you were going to maybe tell us to subscribe to a YouTube channel or something. No, always be curious. Brilliant. Love it. Right, okay, we're going to be back in 167 hours for another episode of the Oxford Online Maths Club coming to you next week on Pi Day. We'll be back for that. Then, other than that, have a nice evening. Have a nice weekend. Take care, everyone. Always be curious. Bye.
Bye.